All right, welcome everybody. And we are from Neo4j, the graph company. So graphs is what we breathe and live for. My name is Mats. I'm the engineering lead for the Cypher for Apache Spark team and Neo4j Morpheus, the commercial product that's powered by Cypher for Apache Spark. And I'm joined here with my colleague Alastair, who is the product manager for Cypher and or for query languages at Neo4j, and also for Cypher for Apache Spark and Cypher for Gremlin and Neo4j Morpheus.
Thanks very much, Matt. So we want to talk about Neo4j Morpheus, which is a product that's in gestation. It's not actually available at this point. It will be very soon in an early adopter release. It's based on Cypher for Apache Spark, which I think some of you will have heard about from the talk yesterday. And the idea is that we want to enrich the graph capability of Spark and combine SparkSQL with Spark graph querying, and also add features that will let us interweave existing data types like tabular data or document data, JSON and so forth, with graphs, and go back and forth between the familiar SparkSQL environment and the emerging Spark graph querying environment. And that also opens the way to integrating analytical activities on graphs alongside the existing transactional operational database capabilities of Neo4j, which some of you may be familiar with. And in the course of this work, we're also beginning to manifest for the first time a lot of work that's been going on within Neo4j, but also within a much broader community of researchers and vendors and users who are interested in graph data, work on advancing and making more sophisticated the graph query languages that currently exist. So we have the language Cypher implemented in our products and in Cypher for Apache Spark. There are other languages like Oracle's property graph query language, which is actually very similar to Cypher. There's been some interesting research work going on in a body called Linked Data Benchmark Council, and some of the newer ideas that you can't yet see in, for example, the Neo4j database are beginning to emerge in this project, Cypher for Apache Spark. So, for example, the ability to project graphs and handle multiple graphs and have graph views. But we will see much of that as we go through. So I guess the sort of starting point of the Cypher for Apache Spark project was really there were two initiation points. One was the one that I mentioned, which is language advancement. And if we go into the Spark environment, we need to be able to deal with multiple immutable graphs. It's very different from an operational transactional OLTP store. But the other one was the general sense that amongst many users of Neo4j, amongst our customers, a great deal of interest in how to integrate pre-existing big data virtual warehouse environments with graph data processing. And graphs, I think, have become a lot more mainstream over the last couple of years. We've seen graph data services in the cloud, like the Azure Cosmos DB graph features, or Amazon Neptune. Simple graph features appearing in mainstream databases such as SQL Server, and I think we'll see more of that. New competitors from a Neo4j perspective, very welcome competitors, because we think this is a huge growing category, and we think that it's great that people from all kinds of angles are beginning to look at the issue of graph querying. And there's also a symptom of that is the fact that there's a lot of work going on, which we're also involved in, to add read-only graph querying to the SQL standard. And we see our own operational store becoming something that is used in the majority of top-tier companies across a whole number of vertical sectors like retail or finance, telecommunications, insurance, and so forth. And also, and I think very relevant for this conference, there's an increasing interest in the capacity to run graph algorithms and other aspects of graph compute over graph model data. And people are thinking about, and I think it's very early days in terms of how this is developing, what's going to happen in terms of AI, machine learning, at the intersection of that with graph. So that's the kind of property graph picture, and then we obviously have a massive movement that's developed around Apache Spark, and there's a kind of as we'll see, there's a very strong parallel with the types of problems that we're trying to address with the types of problems and the approach that was taken in Spark 2 with SparkSQL. So data viewed as tables and data frames processed by SQL, however it's actually presented, in function chains using queries and user functions in order to transform immutable tabular data sets. So before going into what that means from a Spark perspective and some of the sort of data integration aspects that we have building up in Neo4j Morpheus, very, very quick sort of reminder, or maybe an introduction if you're not familiar with this, to the property graph data model made up, to begin with, of nodes, which are entities, if you like, from an entity relationship model perspective. Those can be labeled. There can be multiple labels on nodes. There can be relationships expressed directly between those nodes. So unlike in a relational model where relationships are either implicit between foreign key and foreign key relationships targeting primary keys, or may be modeled using linked tables, relationships are modeled within graph directly, and relationships are just as important as the entities, as the nodes. And in fact, that's the whole basis of graph data management, is to give equal weight to connections and to serve use cases where the connections between data are as interesting as the values on entities or the existence of entities. Relationships can have one type. You can think of that as being like a label on nodes. And then either nodes or relationships, these elements of the graph can have properties. So this is where we actually put data values, and we have effectively name value pairs, which enable us to connect information of any kind of complexity with these elements within the graph. And we can have patterns in a graph query language like Cypher, where we express in a very succinct sort of ASCII line art fashion the relationships between nodes, the kinds of nodes that are being related. And we'll see in this talk both a use of those patterns for querying in the sense of extracting or reaching data within the graph. But we'll also see some new work that's been going on about using these patterns to define the schema of a graph, the kind of data that can actually exist within the graph. And that was something that was in part driven by work going on in the standards world and in part driven by the implementation needs of Cypher and Apache Spark, where we need a schema in the same way that we have a schema for a data frame. And then we can use those, in the searching mode, we can actually extract information from the graph using Cypher queries. We'll see in this talk that we can do a lot more than that with Cypher as it's being developed within Apache Spark. So another way of looking at this whole picture is today you can take data either out of through a JDBC connection or through SparkSQL out of existing stores which were formed or at least are viewed thinking about data in a tabular or relational fashion. Use SQL to actually operate over virtual tables in Spark memory. We want to move to a situation where there will be graph querying and the similar kinds of capacities, either to take data out of an operational store that's already a graph store, or as we'll see later, to sort of turn tables into graphs and graphs into tables, go back and forth between these two modes. If you look at the sort of tabular view and returning to that point, I've covered really the first part of what's said on this slide, but I think what I want to draw, the reason it's there again is to draw attention to the parallels. So data viewed as graphs made up of data frames. We've got a property graph type, and it includes a schema. To describe the graph type, it can be processed by Cypher, the query language, in user functions, in function chains, and we transform immutable property graphs into output graphs, or actually into tables as well. What does it look like? How's this built up? We've got the existing Neo4j database. We started with a Cypher for Apache Spark project, which is about the language, about the ability to have a type, as I said, for graphs, and to introduce graph queries into the session. We've also got a catalog in which we can store graph schema objects. And then we add, on top of that, something called a property graph data source, which mirrors a data source in SparkSQL. There's one that lets you use Cypher to define a projection of an existing database that might have graph data in it. There is a SQL property graph data source that lets us project SQL data in a federated fashion from multiple underlying data sources into a graph. We have one that lets us write and read data save and and load data from the file system, and there are plans for future data sources. So, for example, the Cypher for Gremlin project might lead to the ability to draw data out of Gremlin databases or cloud services and bring that into the Spark environment. Now, sort of moving towards introducing what Mats is going to talk about, we've got this idea of a Cypher session, which is a parallel to it actually sort of contains from a technical implementation perspective, but I think it's best thought of as a parallel to a Spark session. And within it, there is a contained object, a property graph catalog into which entries can be made, and there are two kinds of entries primarily at this point. One is property graph data source, which lets us define graphs and where they come from, and so during the course of query evaluation we can lazily go out and find that data and hopefully do that in the most optimized way possible, only relating to the data needed by the query. And then we can also define views, and we've described these views as view functions. I think this is the first time actually that graph views have emerged in any graph querying language. I don't think that this facility is supported, for example, in Spark or in the RDF world. And the reason we say function is because these views are parameterizable. So unlike SQL views, they can dynamically be specified to work over different graphs of the same underlying type. And so we can have, as a result of registering things in this catalog, we can have named graphs or named view functions. And that is part of, reflects the fact that in the query language, we can specify the graph that we're working on. We can say from graph and social network, or from graph, and it can actually be a view. And we'll see a lot more of that coming up. So tables into graphs is something we're going to look at here, the SQL property graph data source. When we've got graphs in Spark, all kinds of things can happen in terms of graph queries. And one thing that, if we look at the sort of tables view of things, basically we're saying, let's map tables to the labels that we're seeing on nodes and relationships, and we can think about those sets of those labels as forming types. So there's a kind of mapping from underlying tabular data to the types that are associated with nodes and relationships. That will just very quickly here to just point out, not all the details of this diagram, but the column SQL data sources gives you an indication of the spread of underlying SQL sources that are being, that we're working on at present, and that will probably extend. And the general idea is we're going from those SQL tables through a set of mappings to labels in the graph. And the net result of that is a property graph that contains, logically, node tables and relationship tables. We take all of those principles in terms of forming data coming from, let's say, from a relational database or a relational view over the file system, and we've got some interesting features which let us merge that data on an incremental basis back into Neo4j. And in the future, we might look at doing things the other way around and merging or synchronizing data from Neo4j into the Spark environment. That's something that people have expressed interest in. So I'll pass over to Mats to talk about the demo that actually I think illustrates a number of those features.
Right, thank you. So in this demo that I'm going to present, we have a customer 360 scenario. So we have an imagined business, and there are some customers in this business that are interacting with our customer representatives on some accounts using some policies. And the data then is stored in our data lake in some denormalized format, maybe as from an Excel sheet or something else, just dumped as a file that's viewed as like a continuous stream of data that's coming in as interactions happen in your business. And now we want to do some graph analytics over this data to find where we have pain points in our business that we want to focus on. So this is, we do a whiteboard session, and we find that, okay, so we have some interactions with between customers and customer reps, and these little speaking bubbles here show what kind of data points these different node types, the actual data is, what actual data is contained in this, in the graph that we want to extract. But it turns out that our data actually probably looks a bit like this. does not look much like a graph, right? So it's just a flat file of rows. And as you can see here, so there are some interaction IDs that happen during some dates. So how do we get from this file into this graph? Well, as you can see here, we have some patterns, as we call them. You saw on Alastair's previous slides that you had the parenthesis, and then you drew a little ASCII Art arrow down to another parenthesis that's loosely representing these bubbles and arrows that you can see in this picture. And we have a language then that we call graph DDL, and we can specify these patterns to describe the schema of a graph. So similarly to I had after our whiteboard session, we had this graph. We can just specify this as a graph schema. So interactions have just one policy, but several interactions can have the same policy, and the same for customers, customer reps, etc. in our graph. And if you think this looks like an entity relationship model, that's not an accident. An entity relationship model is in fact something that you can view as a graph. And what's missing in this, these 4 lines of schema patterns is the little speaking bubbles of data points. Those we've defined up here. So for every label, we define what kind of data points, again with this pattern-like syntax. And we also define the keys that uniquely identify a specific customer, similar to primary keys in the SQL system. So just starting out in our demo, we're initiating a CAP session here. It's similar to the Spark session. In fact, it wraps a Spark session. And similarly to how you can on the Spark session, you can do .SQL and send SQL queries in. On the CAP session, you can do .Cypher and send Cypher queries in. And what you get out is either a tabular result or a graph. But how do we get from this via these schema patterns to an actual graph? We have to do some preparatory steps. And that we can do with normal SparkSQL processing. So what we do is we create some Hive external tables for the CSV file, the data frame that we load. And in this example, I don't have a continuous stream of data that progresses as time. I just have static data. But let's pretend that we are at the 1st of January of 2017 today, and we're only looking at, so we're creating views over these different data, these different nodes, so that we have the interactions in one view, the customers, account holders, policies, and customer reps in their own views, so that we can map them into the nodes in our DDL. You can see here, so policy comes from the policy seed view, customers come from the customer seed view. This is SQL-like syntax for mapping data from any SQL system. Could be Hive, could be a relational database like Oracle or MySQL. And in fact, you can combine, so you can take some data from Hive and some data from another JDBC interface system. Anything that speaks SQL can interact with this language. So we set these things up in Hive, and then we define our property graph data source, and we just specify where the file is, and it's some configuration on it. I'll actually start running this now. And here we register this property graph data source under a certain namespace in our CAPS session. And this is how we turn the graphs that it manages. I didn't show you this in particular, but here we say create graph. We give it a name with the schema interactions. So the schema we created here at the top, create graph schema interactions with those schema patterns that I showed you. So this means that we're mapping from a relational layer into a graph schema. And this graph is then available in the property graph data source and can be referenced from Cypher queries. We also add another, I'll try this again. We also add another property graph data source for a Neo4j graph database that we want to move this graph over into. So we want to seed this customer data, and we want to move it over to Neo4j for integration or real-time queries that we want to do over this. So once we've done that registration, we can just request to get this graph from our graph data source. So we go to the namespace, we get the interaction seed graph, and we get it into a variable here. And this is all lazily executed. It won't actually do anything just yet. It's part of the Spark lazy data model, and the property graph API that we defined actually underneath the hood is a set of data frames, so it's a set of tables. And that's the key mention that we've done here, is that we can view a set of tables as a graph. So that's true for any set of tables, if you just give us the metadata and to tell us how those tables relate to one another. And then we're moving over this to Neo4j through this Neo4j graph merge tool. So we take this, merge this into the Neo4j, and then we can inspect this from the Neo4j browser. This is the standard Neo4j tooling, and we can see that currently it has now 8,000 nodes. And what this demo just printed here is the output of a graph query here, the Cypher query that we processed on the CAP side and the Spark side. And it printed this table of interesting or potentially interesting customer interactions. So we say that, so customers that interacted with customer reps, we group on customers and the type of interaction. We count the number of such interactions where the type was either a cancellation or a complaint, a potentially problematic interaction. And we print the top 20 such customers. And what you can see is that this is the same graph query language as we have for Neo4j. So you could just take this, paste it in here, and you'll see, if I just expand this a little bit, that we have the same results. So the same graph query language on both sides. So here you can pick and choose whether you want to run your queries on the transactional database for real-time querying, or whether you want to do it in an offloaded scale-out system such as Spark. And if I continue this, maybe we don't want to focus on the customers, but we want to focus on the customer representatives. Similarly then, we go into the session, we say, by the way, from this graph, I want to match the same pattern, but I'm grouping instead on the customer representatives to see how many complaints that they handle. And then I order by the most busy customer representatives. I see there is a Basil Tramer here who's handled 35 complaints. Maybe we should go and talk to this guy to see what kind of help he might need. And if, again, I can just take this query and see that we get the same results if we just paste it in Neo4j browser and run this on Neo4j. But now, time progresses in our demo. We get some new data in. We're at a new point in time. We want to get this over to Neo4j so that we can keep it in sync with the data stream that comes into our data lake. So now we're looking at the interactions delta. This is a graph we defined in our graph DDL, a little bit below here. So with the same schema. So it has the same schema. It's the same kind of graph, but instead now it comes from views that are kind of delta views. They only show the next set of records from the next point in the next chunk of time that's passed between now and the last time it's synced. So if I let that continue, like this, it's going to go into the catalog, extract that from those other views, and move it over to Neo4j. And then also here we can just, if we run this, we see that the count is now 38. So now it's completed the synchronization, and we can keep this job running at intervals that make sense to us for our domain and our business. And you see the same results happen here. So on the Spark side of things, we actually didn't have the entire graph at one point in time, because we just had a continuous stream of data, and we had those views that had date intervals defined over them. But what we can do is we can also take the Neo4j graph. If this query turns out, the queries that we want to process turns out to be very, very heavy and touches the entirety of the graph, maybe that's not what we want to put onto our operational store because it has concurrent transactions happening in real time and they might be blocked by such an operation. So then we want to move that over to the Spark side to do this long-running job, and we can do that seamlessly. We just say, oh, give me the entire graph from my transactional store, and I'll run this query here on the Spark side instead. And it's the same query again, so we can just paste that here. It's the same that we just ran. And of course, you can use all the visualization features of Neo4j as well to kind of inspect the graph and what it looks like. And that, I think, concludes the demo, and we're open for questions for this first part.
All right. Raise your hand if you have any questions, and I'll run the mic over to you.
You were talking about moving SQL data into graph databases and into graph format in Spark. There is a similar or a solution for other databases like Cassandra or MongoDB?
Is there at the moment? No, that kind of comes under the category of the sort of future property graph data sources that we want to build. So you might recall I mentioned the possibility of getting graph data out of a Gremlin supporting data source. And we are very interested in supporting, NoSQL, document formats, document stores, any, column families. The idea of this is to build up the capability to take data from any source and integrate it into a graph. Yeah, but it's not there yet. But this project's got a lot of extra things still to come. It's an interesting area. So yeah.
Okay, so currently there is a number of proposals for graph query languages that tries to standardize the process of graph querying, like GQL by LDBC, Cypher is one of them, but there are also some others. So what is the status now, and is there any progress? So we will have Cypher now and probably another language tomorrow, or that something is going to stand?
Yeah. I was actually planning to talk about that a bit at the end of the second session, but I'll answer it briefly now as you've raised it. So I'm very heavily involved in the whole sort of area that you're mentioning in terms of standardization from a graph query language perspective. The short answer is there is a growing body of support. I was just earlier this week at the International SQL Standards Committee, WG3, where we were discussing how to create a standard graph query language called GQL within the context of ISO, which would be a parallel language to SQL. And we were discussing that in a very concrete way as to what are the measures that will need to be taken, how we will create a proposal and so forth. That's based on a unanimous view within that group that there should be a standard graph query language that would mirror SQL, which is the first time I think that particular database languages standards group has ever looked at another language apart from SQL. And that's the sort of recognition of the significance of graph querying. And the idea is that we will pull in, and this is already happening in an initial stage, existing graph query languages like Cypher, Oracle's PGQL, the research language GQL. There are other languages which we're looking at, and people are beginning to participate, for example, who are involved in Tiger Graph's GSQL language. And that those inputs will be taken as the basis for the graph query language. The other thing just to mention, and I can talk about this in a bit more detail in the second half, is the work that's already been taking place now for a good 18 months on graph query extensions to SQL. And you could really think about those extensions as being the first part of a standard graph query language. It's only read-only. And those, just to give you a sort of sense about what does that mean for a language like Cypher or for existing users of PGX, which has the PGQL language, those are the two industrial languages really in the frame. They have been the inspiration for the graph pattern matching and data return features within GQL. So I would expect that the GQL language, as it emerges, will tend to be strongly reflecting the inheritance of Cypher and PGQL and GQL, all of which are really sort of like from the same family. And in that sense, I think we're going to be able to leverage all of the existing base of use of those languages in order to actually end up at a standard which is also going to be much more powerful than those languages, because we're looking at some of the new features, much more sophisticated regular expression pattern matching, composable graph queries, and so forth. So I think the industry direction here is actually, it may not be super apparent because there's a lot of work going on behind the scenes, but there has been a convergence this year around the concept of achieving that graph query language and actually achieving it at the international standards level, which I think is going to be a tremendous achievement for the industry if we can do that.
Okay, just as a follow-up, so there are a number of graph models. So is property graph will be the standard graph models that will be supported by these languages?
The graph query language is GQL is proposed as focusing on the property graph model. The property graph model has turned out to be the model which has become most widely used in terms of graph data management. And what we are actually doing is there's going to be a workshop at the beginning of next year in which is going to be a sort of a sponsored, but well, organized by W3C. And we're going to be talking at that workshop about how property graph querying can interact with RDF, with SparkSQL, what the boundary should be between those two worlds, because what we also want to do is have a kind of productive relationship between these different models and the tooling that's associated with them, so that users can go back and forth between SQL, RDF property graphs, RDF graphs, property graphs, and so forth. So that's very much in the frame. And there's also work going on to think about how GraphQL as a sort of interfacing language could be used. So.
All right, and we have time for one more question from the gentleman back here.
Thanks. When using Cypher and Spark, is there anything from memory management or Spark configuration we need to be careful with?
So on the not in particular. The Spark since the graphs in Cypher for Apache Spark is a set of data frames under the hood. So what you need to, the things that you need to consider are the same as you would consider if you did a relational processing of those data frames in the first place. So in terms of partitioning and parallelization, for example, or memory caching. We're going to go through a phase. I mean, this product is not ready just yet. It has a bunch of features, but we're going to go through a phase where we're going to look at the performance characteristics more closely to find maybe some golden keys that we can provide for the users as well in terms of configuration. But there is no additional configuration that you need to think about other than the Spark session normal stuff.
All right, welcome back everybody. Thanks for joining us for the second half of the Neo4j talk. We've got Mats and Alastair here to tell us more about Apache Spark and Neo4j and graphs. Take it away.
Thanks a lot. Okay, so we looked or made reference to the fact that in Cypher for Apache Spark, you're actually able to do graph query composition. And this diagram sort of illustrates what I mean by this. So if you compare SQL, SQL is a language where the output of a query, a select statement, is a table. So a result set is a table. And sometimes we don't think of it like that because we just think of it as a result set, a stream of records that's going to be consumed. But when we have nested queries in SQL, we have an inner query that returns data to an outer query, then it is a table and we can use it just like a table. So we can effectively inline the production of a table. And that means that the SQL language is composable. You can take a SQL query and you can compose it with another SQL query. Cypher, as it emerged, and the same is true of PGQL, but not of GQL, the research language, has a limitation. And the language was originally designed for the extraction of the values on the properties. So if you are processing a query on a graph and you identify patterns within that graph or data that matches patterns within that graph, it's not much use to you until you can actually evert that data, make it actually externally visible. And the way you do that is to return a tabular representation of the information on the properties. Now, we retain that in Cypher for Apache Spark, but we add the ability to output graphs, to project graphs. Sometimes people think about this as a subgraph, although the projected graph could actually be a subset and a superset of the graph from which the inputs were taken. And we actually enable you to do this, taking inputs from multiple graphs and projecting a graph as well. So the other thing that you see in Cypher for Apache Spark, which we haven't had previously in Cypher within Neo4j, is the ability to pass in a driving table. So it's a very characteristic pattern that you have a table which contains information which is going to cause multiple iterations over the query for each row being treated as the inputs to the query. And in the Spark environment, where we've got SQL available and SQL tables, and we've got Cypher available, and we can go back and forth between these two modes, and we can take a data frame, a table, and treat it as an input to a Cypher for Apache Spark query, and then we can put out either a graph or a table. And as we'll see, that ability to produce the same kind of outputs as we have inputs enables us to then compose. So we can take the outputs of a graph query and treat them as the inputs of another graph query. So if you think about the very familiar sort of function chain approach in Spark, this sort of plays very well to the idea of a query as a function over a graph. And it could be living alongside other functions, user functions over the graph as well. So we want to be able to support all of those kinds of behaviors. That's where the clicker has gone. So from graphs, and here we're actually adding data to an existing graph called social network, to two existing graphs, and we're actually creating relationships between them and then returning a graph which combines the old information, or the information in the two old graphs, with relationships between elements in those graphs to create a third graph. Now, what's going on here is something that people talk about as graph construction. And effectively, it's the inverse of what happens when you match data in a graph. So when you take data from a graph and create a sort of tabular result, you can think of a tabular result as being an input into a graph construction operation, leading to the existence of a new graph. And that sort of duality is reflected in this ability to interoperate between the two data models, effectively. I'll make a parenthetical point, which we were discussing coming up the stairs to this session, that it might look on the surface like a graph has got exactly the same data model as a relational database, and that there's no real difference. So these are just two different views over two different ways of thinking about the same model. There is a difference between a tabular SQL data model and the graph data model, like a hardcore difference, and that is that you can have nodes and relationships, nodes specifically, that have no properties. And in SQL, you cannot have a table that does not have a column. And that reflects the fact that a graph can express purely structure. It could be the structure of the data is what is interesting about the data, not the values that are actually attached to the structural elements. And that's kind of interesting in terms of why it's actually valuable to think of graph data as being a peer of the relational model, and graph querying as being a peer of the relational model. Because you can do anything that you can do in the relational model in graph querying, and you can do a little bit more as well. So going back to the subject of query composition, there are two ways in Cypher for Apache Spark that we can compose queries. We can use this ability to match and then create a table and then just return that table directly, or to use it as the basis for construction of a new graph. And we can also carry out a union operation. Now, I believe where we've got to with the implementation at this point, unless something's changed recently, is that you can do that union operation at a kind of API level, but you can't do it in a sort of Cypher syntax level, which we're also working on extensions to Cypher syntax to support all of this sort of stuff. And that is maybe just worth the parenthetic comment that, like with SparkSQL, there are some elements of API where you can actually break down what you might think of as a sort of monolithic SQL query into API function calls, and then chain those function calls together and so forth. That's not a completed aspect of the Cypher for Apache Spark project to have a sort of full fluent API, but it's part of the direction in which we're going. So very similar to the philosophy that was adopted with Spark 2. And if you're very SQLite, then you can end up with some giant script that's in pure SQL and in capital letters. And if you're very Scalite or Pythonite or whatever, then you can go in the opposite direction with the API. So this sort of business of property graphs being composable and having the ability to output a graph raises the question of graph views. And that also raised the question of something we don't have in Neo4j in quite this way, which is DDL within, or the level of DDL that we see that's emerging in Cypher for Apache Spark. And the things you're seeing in Cypher for Apache Spark are going to start appearing in Neo4j. I can't make any particular statements about timelines, but that's the direction that's going to be going on here. So we can create in the catalog an object which is based on running a query over an existing graph or graphs. That's one way of storing or ensuring that we have persistent access to such a graph. We can also create a view, and here you can see the ability to create a view that has parameters, and one of those parameters is a graph. The second one is a parameter is just a scalar value that's being used in the predicate here, and we don't actually support that yet in the Cypher for Apache Spark implementation, but this is to give you a sense of what's coming. And so this means that we can now operate the same query over the same view over multiple graphs, and we can determine that at runtime at DML point rather than just being able to do it at the DDL point. There's another thing in this slide which won't work if you try Cypher for Apache Spark, and that's return graph of star. That saves you some writing in terms of actually constructing a graph off a simple match statement, but that will come as well. And so you can use these things in a fashion that's shown here. You can say we're working off session, which is the default place that a graph get created in memory. Graph people US, so you can people by country and qualify it with the nature of the graph and the predicate information. And we can just get data from a new graph once it's actually been created. So this illustrates the fact that I've mentioned already, that there's this ability to go back and forth between Cypher and SQL. It can actually go in both directions. So this is you could think of a graph as being a set of tables, and I think we'll see something of that with some hidden relationship information, which makes it very different, and we'll see some of that in the next demo, which leads me to the next demo.
Thank you. Right. So as we saw in the first demo, we set up a kind of streaming or batch job that periodically, I should say, synchronizes our graph database from our data lake. And we're assuming that that's going on in the background now by something else. And in the second demo here, we want to focus on actually doing some graph analytics on this continuously updated transactional database powered by Apache Spark here. So in this session, in this demo, we just initialize our cap session. We configure, we do a little configuration here to connect it with the Neo4j database that holds the transactional data that's continuously updated. And then we go on and we want to snapshot this. So we want to snapshot this to put snapshot graphs on the file system. And we also want to view these through Hive. So in order to do that, we need to create a Hive database. And we do that with standard SQL, just to create the Hive database and tell the property graph data source which database to create Hive external views in. Then we define a few views, and the queries here look much like you saw in the first demo, the same kind of, so we have customers that interact with customer reps, and we look for problematic interactions. But instead of just outputting a table, this time we're constructing a new graph. And it's kind of a roll-up graph. It's an aggregated graph because we're doing an aggregation. We're counting the number of interactions that had these problems types. And now we're constructing a new graph where we say that this customer, it's still a bound variable, so it's not just an empty node. It carries through all the data values from the customer bound by this variable, reported a problem, or several problems in fact, this many problems of a certain type. And we add that into a new graph. And then we have a similar view for the customer representative view where we group on the representatives instead, and we say representatives received a problem. of a certain typing count. And these views are kind of abstract or like stored queries, if you will. You add them to your catalog and you can reference them from your queries. But they take parameters here. So during view creation time, of course, it cannot be evaluated. We don't know the value of the source graph we want to operate on. So it's pretty quick to add to the catalog as a consequence. And then we go on to kind of, okay, so at a specific point in time, we want to snapshot our transactional database through these views. So what we do here is we create a new snapshot graph in our catalog. So we figure out when now is, and we give this one a unique name in our snapshot PGDS. And we say, well, just over the transactional graph, apply the customer problems view, and give me that graph back, store that in the snapshot property graph data source. And I'll run this now. And this is going to output stuff in here. So we see we've taken a bunch of snapshots. I've run this demo several times. Normally, the snapshots would actually contain probably different data, but now my data is static. So all of them are the same, not super interesting, but in a more realistic scenario, you'd see all these snapshots actually be a progression of your problematic interactions over time. But these graphs that you can find through reviews, and then you see some stuff popping up in the console here. That's stuff that comes from here. So as I said, we wanted to create Hive views over the tables that make up these snapshot graphs. So I'm just listing my stuff from my Spark session catalog in the snapshots database. And we see that we have a customer table, a problem table, and reported relationship between these. Similarly, we have customer reps, their problems, and which problems were received by which customer rep. And this is some data that we see from one of those tables. We just output some stuff there. But the graphs that were defined by these views might not be too interesting in and of themselves. So it just says that a certain rep received a problem. It's just a different form of what we saw in the tables in the first session. So why don't we just output those tables? Well, with a graph, we can do a little bit better. We can integrate those two graphs. So we have the customer rep view over the transactional database, and we have the customer side view of it. And we can integrate those with one another. And we'll do that with a similar feature here with the graph merge, where we offload both of those two snapshot graphs into our problems database, which currently contains nothing, I believe. I'll just write a query here and we'll count the number of nodes. And it's empty. But when I let this program continue, it will write both snapshots for a given point in time, for the point in time that we snapshotted now, over to this problems database, and it's done. Now we can see, for example, we can find problems. I can count the queries here, count the nodes. So we have 1,000 nodes here now. And okay, so what kind of problems do I want to look at? Well, I want to look at the problems that are most frequent. So I'll just, where the count is more than 5, and then also want to see what kind of relationship, who reported or received these kind of problems. We can output that and look at this as a graph. And we also had a timestamp here that we put on when this statistic was taken, when this snapshot was taken. And as if time progresses and a transactional database can map more interactions, we can do this kind of snapshotting many times into this database, and then we can do maybe some time analysis for, okay, so and we can enrich it with other information. So we've taken some measures to kind of deal with these problems. Okay, so how effective was that after a point in time, maybe 5 months later? How does the progression of problems in particular customers that we focused on change, or anything? The point here is that we could integrate the fact that we took those views over our mutable graph, then we can turn them into graphs that we put on the file system. We can thus integrate those graphs with one another again. Yes. Back to you, Alastair.
Actually, is it worth just exploding the file system view just to show what's on disk? Because we've seen the Hive tables version.
Yeah, sure. So we can see here. So when we write a graph to disk, it's following a well-known directory structure format. So we have the nodes here, and then we have one directory here for every node type, and it prints a bunch of CRC files here by Spark. Which one is the actual data file? Oh, it's a Parquet format, so I can't view it. It's binary. If I'd used a textual format such as CSV, I could have showed you the data from the files directly. But it also stores like the proper graph schema here. So this is the what kind of graph is stored in this particular directory. Well, it's one where you have problem labels, customer labels, and reported relationships and their data types.
That schema sort of representation is interesting because we saw the DDL earlier on in the SQL property graph data source that lets us write sort of ASCII Art patterns to define the schema. And the information content's exactly the same as that JSON representation. And in a next step, there'll also be the possibility of doing catalog operations that will let you create a schema independently of a graph and then use that schema for the construction of a graph. And I think we actually have that sort of the API level, the ability to attach an independently defined schema object, if I recall correctly. So there's a kind of picture sort of emerging there. The last part of what we wanted to talk about has come up already in a question from the end of the first part of this, but I'll talk about it a bit more detail. So we've got this idea of extensions to SQL for property graph querying, read-only, and we've also got this idea, this initiative that was put forward. I wrote something called the GQL Manifesto back in May, suggesting that the industry should get together to try and actually create a GQL standard. And we can see elements that I think will go into these efforts emerging or being implemented within the Cypher for Apache Spark Morpheus context. So the SQL graph DDL is a kind of prototype or draft of things that are being discussed in the context of the SQL property graph query world. And if you think about the SQL vendors or SQL database vendors, they want the ability to define a graph over existing relational tables to create an object in the SQL catalog or information schema, and that's exactly what we're doing when we map data from the underlying relational stores or from Hive or Hive view over file data or just a SparkSQL in general. So that's something that we're looping over and contributing and discussing with other participants in that particular standards process, and that's heading to be part of the next version of SQL. SQL comes out on a roughly 4 to 5 year cycle in terms of the official standard. The last version was 2016. The next version is probably going to be 2020 or 2021. And then the other thing that you can see here is this graph schema and the composable graph queries are things that are either interesting for both the SQL version of graphs or for an independent graph query language. Composable graph queries is something that there was a lot of work going on between a group of researchers and industry vendors coming together under the umbrella of the Linked Data Benchmark Council, thinking about that problem, and we've been trying to sort of track that from an implementation perspective within the Spark context, first of all. And you could think of those as being, again, sort of premonitory prequels to GQL. And the other thing that's worth sort of just re-emphasizing is that the property graph querying is planned as a very significant subset of a wider full create, read, update, delete graph query language. And I think, as I said earlier on, there's a lot of activity on improved pattern matching and also control over what's called morphism, the degree to which elements within the graph can be repeated in the results that are actually produced. For example, whether or not you get an edge repeated more than once, and being able to actually provide control over that, which is something that has performance implications and also application behavior implications that people want to address. So if we sort of think about the question, that should say from Cypher to GQL, don't know what happened to the 2 anyway. This is kind of just diagrammatically representing what's been going on, the different influences. So Neo4j Cypher, in 2015 we turned into the Open Cypher project. The Open Cypher project has led to about 11, I think, currently implementations of Cypher, 4 or 5 of which are commercial, 5 I think now, are commercial products. The others are research implementations, including, for example, a project that some researchers at HP Labs and Queen Mary University London did on Cypher to SQL, kind of actually related to some of the things that we've been doing in Cypher for Apache Spark. And there are a number of artifacts and tools that are available on an Apache licensed open source basis that people have been collaborating on in that project, which we hope to carry forward to GQL. So one of the things that's likely to be different about GQL or GQL by comparison with SQL or SQL is we're trying to create a community aspect to that standards initiative, and we're trying to make sure that there's a software reflection of the standard that's being defined at a sort of formal written level within the ISO process, and to make sure that some of the benefits that we saw out of Open Cypher are carried forward into that wider world, so that tools like a technology compatibility kit or potentially a reference implementation will be available, as well as the written specification, the idea being that we have multiple artifacts, some of which are assisting artifacts, not normative, and then some which are actually normative for the specification itself. And we have, as mentioned, GCore and Oracle PGQL both being other contributors, and hopefully, as I said earlier on, other databases and languages are going to contribute to this picture. So, for example, the GSQL language from TigerGraph looks like they're coming into the frame and beginning to work in the SQL property graph querying extensions as well. And so you could summarize all of this as heading towards a situation where, from a Spark perspective, we'd like to be able to say Spark.SQL or Spark.GQL. And we'd like to see Cypher for Apache Spark moving towards being the basis for data frame-based graphs that are somewhat richer than the graph frames or GraphX model, supporting Cypher graph queries, and that's the subject of some discussions which may result in a Spark project improvement proposal. And our overall direction here would also be that Cypher would become subsumed or transformed into ISO GQL and as part of that standardization process, and that would lead to this conclusion that there could be both languages, Spark GQL and Spark SQL, and you'd be able to go back and forth between them. And that's also a picture, not just a Spark picture, but an interesting kind of industry picture that seems to be emerging here. So that's the sort of story on where things may go. All of these things are take work and discussion and agreement and consensus, difficult things to achieve in the vociferous world of the software industry, but we're doing our best. And I'll just finish by talking about the actual timetable for Neo4j Morpheus. So effectively, it's going to be a commercially supported edition of Cypher for Apache Spark. So all of the components of Cypher for Apache Spark, everything that we've shown you here today is going to be open source licensed, or is open source licensed. Not everything that we have that we've shown you today is yet in the Cypher for Apache Spark project, but that will be happening. And we will be commercially supporting a certified sort of binary package of Cypher for Apache Spark, support different Spark distributions, certified against different SQL data sources, and so on and so forth. Over time, there may be closed source components that arise within Neo4j Morpheus, but to begin with, it's going to be that picture. And we've got a early adopter release scheduled for the end of this month. So you can sign that up for that, and for the link shown here, and there's documentation already available as preview documentation. And then the things that are coming, as Matt said, Cypher language feature expansion, because Cypher is a big language, and we haven't covered all of the existing Cypher 9, the sort of the pre-graph construction version of Cypher yet, and we haven't finished all the things we want to do in terms of the more modern features. And there's a lot of performance and scale testing and so forth that we want to go through before actually putting company resources behind supporting a paid-for product version of this. So we're heading towards some point in the first half of 2019. Neo4j Morpheus should be available as something that customers can add on to their Neo4j Enterprise edition licenses. Did you want to show the user guide thing at all, or are we done?
I think we could be done here.
I think we're done. I think we're to questions if we have any more time.
Thank you.
Let's give him a round.
Thank you. The question is about scaling and performance. Neo4j is optimized to index the data, so queries with multiple hops can be optimized given certain filters and restrictions. How do you address this while using existing tables which are not indexed or optimized for multiple hops query in Cypher? How would it scale? How would it perform?
Do you mean on Spark or
on Spark? Yes.
On Spark, right. So I mean, since on Spark we have tables, so hops between different nodes constitute joins in the relational world. And you can do also like arbitrary amount of hops, or at least up to a certain bound, which constitutes like a long series of joins. And that performs just like joins in SQL performs.
But so the advantage of Neo4j in this account is the adjacency of the...
Maybe.
The advantage of Neo in this account is the adjacency of the elements near every node. So how would you boost performance of tables which are not indexed for these kind of queries? Because join means shuffling, and shuffling is very highly cost. Do you plan to create additional tables which are better indexed for queries?
Yeah, maybe I can pick up part of that. I think, so first of all, you're right, all facts. Second of all, we're at the sort of early stages, and so the actual concrete answers to some of these questions about what are the best opportunities for optimization, related questions like the best strategies for partitioning and so forth. I mean, sort of high-scale partitioning, not graph partitioning, not just table partitioning, is something that we're going to be working on. And so the emphasis has been largely on functionality and being able to actually provide the first pass on the problem. And I think the team have some ideas, and I think there are a number of areas that we can explore. But I suppose at some level, you're exposing one of the reasons why we created Neo4j as the primary Neo4j database was actually to have a underlying architecture in terms of storage, which would optimize for indefinite, infinite length traversals, and there are trade-offs here, and there are going to be use cases where we're probably never going to be able to do what we will never be able to do in Spark what we can do from a performance perspective, in a single machine in memory, right, in Neo4j. And this is the other side of the flip side of the other thing that people are always asking us about Neo4j, which is how do you get horizontal scaling in Neo4j? And so the problem is, of the trade-off, right, and what it means in terms of taking network communication hits, it's very difficult. And there's also a problem that's even more complicated in Neo4j, which is how do you do graph partitioning in the face of change of the data? And so one of the reasons why we have not answered those problems in running software as yet is because nobody's answered those problems in running software, and they're very, very difficult problems to work out the right kinds of, the right trade-offs, right kind of workloads and optimizations. This is all part of a bigger picture, because from a product perspective, we are moving from having a database to having a graph data management platform, and we are trying to explore the edges and the spots where we can hit good ways of doing good things for good workloads and make graph data something that you can work with across that whole space. So we don't pretend to do things we can't do. We don't pretend we're more advanced than we are at the moment. But we're very conscious of the issues that you're raising questions about. So, yeah. Yeah, please.
How would you compare Neo4j versus JNS Graph / Titan? I mean, what kind of use cases you would use one way or the other?
Well, take JNS Graph. I mean, JNS Graph is a open source project. It's based on what was called Titan, and it's based on Gremlin. And Gremlin is based on the idea that you have a backing store, which you're not quite sure what that backing store might be, and the characteristics of that backing store will help inform the characteristics of the resulting database. So, for example, if you use a non-transactional, non-ACID store, you can't have transactionality. If you can't have transactionality in graphs, it's disastrous, actually, because you get graph corruption. So there's something different. Another thing that's different about graphs from the relational model is that the data model itself is violated by a failure to enforce a consistency constraint, which you could think of as a relationship as being. So JNS Graph, in that sense, is a kind of gives you a vehicle to sit on top of existing stores and work with them. The closed source versions of exactly that same approach are what are used in Cosmos DB and Amazon Neptune. All of them share the characteristic that they expose a language, which is the Gremlin API, which is much more of an imperative language, procedural language, doesn't have the sort of declarative querying capabilities that we've been looking at here. And so we don't see that as just two approaches in terms of the APIs, but we think that it's much, much harder, and developers' experiences find it to be so, much, much harder to work with Gremlin than it is to work with a declarative language like Cypher. So those are two areas in which there's a difference as far as JNS Graph is concerned. It looks like we're running out of question time, are we? Yeah.
That's all the time we have, unfortunately. Thank you, Neo4j team, for joining us today.